Good morning, welcome to new lecture. Today I will solve different example problems. We have two shafts and they are thin walled shaft. One of them it is closed section. So we have a shaft, it is closed section and it is thin walled. The thickness is T, average radius it is R, and it is thin walled closed section. This shaft we call it shaft A. We have another shaft. This is again thin walled shaft, very similar to the shaft A. The only difference, this is open section, you see. Here, it is open section. Other than that, it is identical. So they are identical. Thickness is again T, radius is R. We call this shaft B. So shaft A and shaft B, they are identical. Radius is the same, thickness is the same. The only difference, one of them is thin walled closed section, another is thin walled open section. And problem statement says assume thickness is equal to 1/10 of radius. So thickness is equal to 0.1 R. We call this open section shaft B, closed section shaft A. And we apply torque in the center T. The magnitude of external torque we apply it is T. We want to find maximum shear stress in shaft B over maximum shear stress in shaft A. We have these two shafts, we apply the same torque. We want to see maximum shear stress in shaft B over shaft A, the magnitude, what is the ratio of the maximum shear stress in shaft B over shaft A. This is unknown. We want to find this. Let's look at the problem. We know for closed section, thin walled closed section, if it is subjected to the torque, we will have shear stress, and shear stress it will be torque divided by 2AT. So shear stress in shaft A will be equal to torque T divided by 2AM. AM is area enclosed by mid-surface times T thickness. So here shear stress in shaft A will be T divided by 2AM times T. This will be equal to T times 2. The enclosed area by mid-surface will be pi R squared times T. Shear stress in shaft B. Shaft B it is thin walled section, but it is not closed, it is open. So it will be similar to the rectangular cross section. Rectangular cross section, the length of this rectangular cross section here, it is the length of this curve. The length of that curve will be 2 pi R. The height of this rectangular will be thickness of that, it will be T. For this case, if you remember, the formula shear stress was T divided by 1 over 3 A B squared. Here, long side it is A, the short side it is B. This will be T 1 over 3 2 pi r times E squared will be T squared. So ratio of these, so if I take ratio of tau B over tau A, it will be T and T, they will cancel each other. It will be 2 pi r squared T 1 over 3 2 pi r T squared. From here, if I simplify that, it will be 3r over T. So the ratio of tau B over tau A will be equal to 3r divided by T. Problem statement says thickness is equal 1/10 of radius. If I plug that, this will be 3r divided by 0.1 r, that will be equal to 30. Magnitude will be equal to the 30. So tau B over tau A finally will be equal to the 30. So these two shafts, they are identical. The only difference, one of them, it is thin walled closed section, another it is thin walled open section. We apply the same torque. If we apply the same torque, shear stress, maximum shear stress in torque B will be 30 times higher than maximum shear stress in shaft A. So shaft B will be much weaker and shaft A will be stronger shaft. Let's look at another problem. We have shaft. The cross section is open section and it is triangular shape. So it is triangle. Assume triangle. This is the cross section of the shaft. We apply torque. It is open section, shape similar to triangle. So the length of this leg, it is A. The thickness is 2T. Length for here, this leg, it is A. Thickness is T. Length for this leg, it is A. Thickness, it is 3T. We apply torque T. We want to calculate maximum shear stress. We want to calculate maximum shear stress. Maximum shear stress, this is again, is because it is open section, it will be a torque we apply to the rectangular cross section because it is open. If it was closed, it was another story, but because it is open section, so we will call this rectangular cross section subjected to the torque. Rectangular cross section subjected to the torque formula, if you remember, was T C1 A B squared. C1, as I mentioned, if A over B is greater than 10, C1 roughly is equal to 1 over 3. And here it is thin walled, so C1 it is 1 over 3 T divided by 1 over 3 A B squared. But here the thickness, it is not uniform thickness. Once it is not uniform thickness, we can modify this formula. So it is not constant thickness in entire length of this rectangular, so I can write shear stress is equal to torque times the thickness of that part. I want to find shear stress in that part, divided by 1 over 3 summation of I is equal to 1 to n AI BI cube AI BI cube. So if it is uniform, you see it will be simplified to this. If it is uniform, it will be T times T 1 over 3 A. This is here I should write, sorry, B. It will be T times B A B cube, and B they will cancel each other. Formula will be T divided by 1 over 3A B squared, the same formula. So once thickness is not uniform, we can modify formula. Here in this case, because we want to find maximum shear stress will take place in the maximum thickness location, you see, because we will multiply to the B. Maximum thickness is here, so it will be T times 3T divided by 1 over 3 A T cube plus A 2T cube plus A 3T cube. Answer for this will be equal to tau max. If we simplify all terms, it will be torque divided by 4 A T squared. So, if we apply torque to the rectangular cross section or thin walled cross section which is open, again it is kind of rectangular cross section, in that case shear stress, if the thickness is uniform, in that case shear stress will be torque divided by C1A B squared. If A over B is greater than 10, in that case I can write T over 1 over 3 AB squared. If we apply torque to the cross section, it is rectangular cross section or it is thin walled cross section, but it is open thin walled cross section, and thickness it is not uniform. Each part has different thickness. In that case, I can modify that to the T B, and if A over B, again it is greater than 10, 1 over 3 summation of from 1 to n AI BI cube. It is the same, so that was the only difference. Let's look at to another problem. We have two shafts. Support condition and external torque, it is identical, same. We have shaft 1 and shaft 2. Material is the same, length is the same, everything is the same. The only difference, it is in cross section. External torque, sorry, it is not the same. External torque in the shaft 1, it is T1, in the shaft 2, it is T2. Cross section, this one, it is thin walled open section. Thin walled open section, and each part it is A, and it is a square shape. Cross section, it is thin walled open section, and it is a square shape. For shaft 2, it is thin walled open section, but shape it is triangle, like this. So each part length it is lowercase a, each part length it is again lowercase a, both of them thin walled, both of them open section, length same, shear modulus same, so material properties the same. We apply torque T1 in shaft 1, free end, and torque T2 at the end of shaft 2. Problem statement says if the twist angle at free end, is equal, what is the ratio of tau 1 max over tau 2 max? So the twist angle at free end is equal. We know that. If twist angle is equal, see what is happening. Twist angle for shaft 1, phi1, is equal to T1 times L divided by G times J. J for this case will be, it is rectangular cross section, it will be 4A T cube over 3, because it is thin walled, the C2 coefficient it is again 1 over 3, so the length it will be 4A, the thickness is T, so the thickness is T, thickness cube over 3. This will be twist angle at free end for shaft 1. Twist angle at free end for shaft 2 will be T2 times length divided by G times 3A 3 cube over 3. Problem statement says twist angle it is equal. So phi1 is equal to phi2. Problem statement says if the twist angle at free end is equal. So phi1 is equal to the phi2. If we put these two equal, L and L they will cancel each other, G and G they will cancel, and if we simplify from here, we can find T1 over T2 ratio is equal to 4 over 3. So T1 over T2 ratio, it will be equal 4 over 3. Now, shear stress maximum in shaft number 1 will be torque in shaft 1 over 3 length 4A thickness squared T squared. Maximum shear stress in shaft 2 will be torque in shaft 2 T2 1 over 3. The length for this cross section is 3A T squared. Now from here, if we find the ratio of tau 1 max over tau 2 max, we should write T1 divided by 4A T squared over 3. Here T2 divided by 3A T squared over 3. And we know the T1 over T2 ratio, it is 4 over 3. We can plug from here. And A cancel T squared. So you see this A, they will cancel each other, T squared, 3 and 3. From here, this will be 4 over 3 times, let's see, it will be 3 over 4, sorry, 3 over 4. It will be 3 over 4 times T1 over T2, because T1 over T2 it is 4 over 3, so instead of this, if we plug 4 over 3, I can write 3 over 4 times 4 over 3, that will be equal to 1. So the ratio of tau 1 max over tau 2 max will be equal to 1. Let's look at another problem. We have one solid shaft. So we have one solid shaft. Cross section is circular cross section and it is solid shaft. We clamp at the ground, so this is fixed support. It is subjected to the torque T naught at the center of cross section. Diameter here, it is D. The length is 2L. Here it is point A, this is point B. At point A and B, we have rod, both end is hinged. So the plane for this shaft and plane for this rod, they are perpendicular to each other. It is three-dimensional problem. They are not in the same plane. The length of this rod is L, Young modulus E, area A, L, E, A. Shear modulus for this is G, polar moment of inertia is J. But problem statement says G, J for this shaft is equal to E, A, E squared. So the magnitude of Gj for the shaft is equal to Ea times d squared. We can plug instead of Gj, Ea, d squared. Problem statement gives that number to us. This is the shaft. These are rod, both end pin, and this shaft plane and this rod plane, they are perpendicular to each other. It is 3D problem. Problem statement says determine the axial force inside of this rod F. What is the axial force inside of this rod? So what is happening? We have the shaft. Here we fix to the ground. We apply torque T naught. If we don't have this rod, what will happen? This cross section will rotate. So point A will come to here. Point B will go to here. So point A will come here. Point B will go there. And how much will be the this length and this length. We can find that because we can find the twist angle. Twist angle is phi. If we don't have these rods, if we apply this torque, A will move to the A prime, B here, point B, will move to the B prime. And we will have twist angle phi here. Now, because we have this rod, if we apply this torque, A wants to come to the A prime, B wants to go to the B prime, but that deformation will produce axial deformation in this rod. And because of axial deformation in this rod, they will show reaction. They will show reaction force and they will not allow to move freely. So that reaction force F, it once retained to the initial position. Now what is that internal force in this rod? We should solve this problem. It is easier to solve using superposition. Assume we don't have these rods. These rods, we don't have it. And if we apply torque T naught, what will be twist angle phi? Twist angle phi, if we don't have it, these rods will be T naught divided by torsional stiffness of the shaft, which is Gj over L. Let's I call this phi 1. So if we don't have these two rods, if I apply torque, this twist angle, phi 1, will be equal to T naught divided by torsional stiffness of the shaft, Gj over L. Now, this twist angle will produce deformation, so this arc deformation we will have. And that deformation, it is same deformation, axial deformation for these rods. How much is that deformation? That deformation will be phi 1 times the radius of this shaft. Radius of the shaft is d over 2, because it is a small deformation, so we can write that deformation, it will be phi 1 times d over 2. Because of this deformation, we will have axial force in these rods. The axial force in these rods, the magnitude, it is unknown. I assume it is F. Okay? So I assume it is F. That force will produce another, that axial force will produce, if we apply F and F here, that F will produce another torque contract with this deformation. That torque magnitude will be force times the radius F times d over 2 plus F times d over 2, because this is F times d over 2 plus F times d over 2. Entire torque will be Fd. Entire torque will be Fd. Because of this torque, Fd, this torque will produce another twist angle in this cross section in inverse direction. That twist angle will be, I call it phi 2. it will be Ft divided by, again, torsional rigidity of the shaft, it is, or torsional stiffness of the shaft, it is Gj over L. And this twist angle, it is in inverse direction. If this twist angle, it is counterclockwise direction. This one, it will be in clockwise direction. And this phi2 will produce another axial deformation, or another, instead of going to the B prime, it will return from B prime to this point, B zegon. That B prime B zegon magnitude will be minus phi2 times, again, D over 2. Finally, deformation in these rods will be equal to axial force in this rod divided by axial stiffness of the rod. So from here, if I plug everything, I have T naught Gj over L for phi1 times D over 2 minus, for phi2 I have Fd Gj over L. Sorry, this L, the length of this shaft, it is 2L. I should plug, this is 2L, this is 2L, this should be 2L. So this will be Gj over 2L times D over 2 is equal to F divided by EA over L. If instead of Gj, I plug EAD squared here and here, and take this term to another side, to the right side, and find F and simplify, I will end up with F is equal to T naught divided by 2D. In order to understand this problem better, I should draw one top view picture for you. If I draw that top view picture, you will understand better. Top view, this is the cross section of the shaft. This is one rod. This is another rod. We apply torque T naught here. If we apply torque T naught here, what will happen? If we don't have this rod, this is point A, this is point B. If we don't have this rod, this point A will move here A prime, and this point B will move here B prime. And this will be twist angle phi1. Now, phi1 times radius, which is D over 2, will give us AA prime. So, this is A prime term. This is AA prime term. So, twist angle phi1, once we don't have this rod, is equal to torque divided by torsional stiffness of this shaft, which is Gj over 2L. Gj over 2L. So if we don't have these two rods, AA prime will be phi1 times D over 2. From here to here it is D over 2. That will give us AA prime. But because we have these rod will produce force F, reaction force F, and F. They will not allow to point A move to A prime because they will apply reaction force. That reaction force F times d over 2 plus F times d over 2 will produce another torque here in inverse direction. That torque magnitude, it is F times d, because internal force in this rod, F times d over 2 plus F times d over 2 will be Fd, and that torque will be in inverse direction. That torque will brought back A prime to another point, for example, A2 point, and B prime to another point, for example, B2 point. So this angle, okay, this angle here, this small angle, will be phi2. It is equal to this torque, Fd, divided by torsional stiffness of this shaft. Now, you get to see what is happening. First, A move to the A prime, then A prime A2. It will return this much. That much it will be phi2 times again d over 2. This is A prime A2. Finally, we have this angle phi, which is equal to F divided by axial stiffness of that. So if I draw picture one more time bigger, A, B, A prime, B prime, this is phi1. Then, this is because of the torque T0. Then, another torque Fd will return A prime to the point A2, for example, this much. This is phi2. Phi1 minus phi2 will be equal to this angle phi. This angle phi times this angle phi times d over 2 will be this deformation. That deformation is axial force in rod divided by axial stiffness. So if you understand the concept, you can solve this. Again, try to solve this problem yourself. If you cannot do yourself, or if it is not clear what I did here, send me email. I will explain this problem one more time. Let's look at to another problem. We have composite shaft. It has inner part and outer part. Or we have shaft made using two different materials. Young ones for inner one, it is G1, and radius it is R1. For outer one, it is G2, the radius it is R2. So side view will be like this. This shaft The length is L. This is shaft, this is the cross section. From center to here, it is R1. From center to here, it is R2. Material property, for this it is G2, for this it is G1. We put one rigid plate here and we apply torque T. We apply torque T to the rigid cap or rigid plate. And both material we attach to this rigid plate. So we apply torque. This torque T will be distributed between this inner one and outer one. Problem statement says find G1 over G2 ratio so that tau 1 maximum is equal to tau 2 maximum. And problem statement says R2 is equal to 3 times of R1. So we have a shaft. Shaft is composite shaft. Inner part and outer part. Inner part it is solid shaft. Outer part it is hollow shaft. We put inside of each other. And once we apply torque, they deform together. The R2 is equal to 3 times of R1. Material property for inner one is J1, for outer one is J2. Radius of outer one it is R2. Radius of inner one it is R1. We put one solid cap and we attach both shaft to that solid cap. And we apply torque T. We apply torque T at this cap. So this is rigid cap. We attach both these material to this cap and we apply torque T. So they will deform together. Problem statement says find G1 over G2 ratio so that tau 1 maximum is equal to tau 2 maximum. Tau 1 it will be T1 R1 over J1. Tau 2 it will be equal to T2 R2 J2 over J2. Because we know for solid shaft, shear stress is equal to torque times radius over J. Here, because we have two different parts, for part 1, torque for part 1, contribution of the part 1, times the radius of part 1 divided by polar moment of inertia of part 1. For part 2, it is contribution of part 2. This T will be divided to the T1 and T2 part. We don't know the contribution of T1 part, contribution of T2 part, but we know the summation of T1 plus T2 should be equal to total T, total torque we apply. We know that. It should be equal. Now, problem statement says the maximum shear stress in shaft 1 and shaft 2 should be equal. If we put these equal, what we will get? That should be equal. But once we apply torque and they form together, twist angle at the end should be equal to. Twist angle should be equal to. Twist angle for shaft 1 Phi1 is equal to T1 L over G1 J1. Twist angle for shaft 2 should be equal to T2 times L G2 J2. Because they deform together, twist angle should be equal to. So instead of phi1 and phi2, we can write phi. Because phi1 should be equal to phi2, we can call it phi. From here, I can write T1 is equal to G1 J1 over L. T1 is equal G1 J1 times phi over L, and T2 is equal to, from here, G2 J2 times phi divided by L. I can plug this T1 here. I can plug this T2 here. So if I do that, I can find ratio of tau 1 over tau 2 is equal to, it will be equal to G1 J1 over L times phi R1 over J1 divided by G2 J2 divided by L times phi R2 over J2. This is equal to phi and phi, they will cancel. L and L, they will cancel. This J1 and this J1, they will cancel. J2 and J2. So finally I can simplify to take G1 R1 divided by G2 R2. So finally I can simplify to, for this case, tau 1 over tau 2 is equal to G1 R1 divided by G2 R2. Now we want to find G1 over G2, that is unknown. So we want to find G1 over G2 ratio so that tau 1 and tau 2, they are equal. So tau 1 and tau 2, if they are equal, they will cancel each other and it will be equal to 1 times R1 over R2, R1 over R2. R2 problem statement says it is 3R1. Instead of R2, I can put 3R1. So from here, R1 and R1, again they will cancel, and finally I can find G1 over G2 ratio is equal to 3. So if I have a composite shaft, inner part with one material, Young modulus, it is J1, and outer part it is J2, and radius for inner part it is R1, for outer one it is R2. If this system is subjected to the torque at free end, and we put one cap here, we attach both material to that cap and we apply that torque, they will deform together. We want to find G1 over G2 ratio so that the maximum shear stress in inner part and outer part are equal. They should be equal. In that case, we should select the material property like this. Young modulus ratio of material 1 over material 2 should be equal to 3. And this is given. R2 is equal to 3. R1 is given in problem statement as well. Let's solve one more problem, and I think it is enough for today. we have two different sections for shaft. One of them thin-walled closed section like this, another open section like this I section. The length for this are, the thickness is T, R, T, radius for this R, and the thickness is T. And we know R over T is equal to 10. We want to find torsional strength of, this is shaft 1, this is shaft 2. We want to find torsional strength of shaft 1 over shaft 2. Torsional strength means what is the maximum torque we can apply to this shaft. What is the ratio of maximum torque we can apply to the shaft 1 over shaft 2. Torsional strength means what is the maximum torque we can apply safely to that shaft. What is the maximum torque we can apply to that shaft before failure or yielding, that depends. And material property is the same. Material property, both of them, for example, made by copper. If material is the same, allowable shear stress, that shear stress, it can reach maximum, it should be the same. So allowable, I show it top and this A, allowable shear stress, it should be equal to material property is the same. So the shear stress in section 1 will be torque divided by 2 AMT. From here, torque will be tau times 2 AMT. Torsional strength for shaft number 1, T1, will be allowable shear stress, maximum allowable shear stress we can apply to this shaft times 2 times area enclosed by mid-surface. That will be, it is half of one circle, pi r squared over 2 times t. This will be equal to tau allowable pi r squared t. For shaft number 2, because it is shaft number 2, it is open section, T2 summation of L T squared over 3. From here, T2 is equal to tau allowable times summation of length thickness squared over 3. That will be tau summation of thickness is thickness times t squared. It will be rt squared plus rt squared plus rt squared, 3r t squared divided by 3, it will be r t squared. And because material is the same for both shafts, this tau allowable will be equal to this tau allowable. And from here, the torsional strength ratio T1 over T2 will be equal to, if I divide this by this, tau and this A, they will cancel each other, and finally it will be pi r over t, and if instead of r over t I plug 10, it will be 10 pi. And because pi is equal to 3.14, it will be equal to 31.4. It means if we make shaft with the same material, one cross section is like this, another cross section is like this. This cross section is 31.4 times is stronger than this cross section. Cross section 1, 31.4 times is stronger than cross section number 2. If the same material we have and we apply torque, this one is stronger 31.4 times than this one. That is the meaning torsional strength. In torsional strength, it means what is the maximum torque we can apply to that cross section. Okay, thank you so much for watching this lecture. See you next session. Bye bye.